So now we will study another property of a convex function that will become useful once we prove the first order convexity condition for any function f. So let's see what this condition is. Sorry, what this property is. So it follows naturally from whatever we have discussed so far. It follows naturally that f is convex if and only if when f is convex when it is restricted to a line that intersects its domain. So f is convex if and only if it is convex when restricted to a line that intersects its domain. So this is one important and very useful property of a convex function, and it becomes very useful when the original function f, if you have to prove that the original function f is convex and it is very hard, then what we can do is that we can convert, we can restrict that function to a line so that it becomes a mapping from a scalar to some scalar value. And then if we can prove that the resulting function is convex, then the original function f is also convex. So what it means is that if the function g of variable t, which is equal to f of x plus t times v, f is convex if and only if g of t is convex, subject to condition that x plus t times v, it belongs to the domain of f. So the domain of the function g of t, the domain of g is set of all t such that x plus t times v belongs to the domain of f, where v is some direction variable. For example, what this condition actually means? So for example, we have the domain of the function, which is a convex set. So we select any point x in this domain. Now there are different direction vectors. For example, this v is one direction vector, this is another direction vector, this is another direction vector, and likewise this is another direction vector, and likewise this. So for one special case, for example, if we select this point x, and so this is our direction vector, right? So we can scale it up with some t such that it extends all the way up to the two opposite ends of its domain, right? And if we can prove that the function f is convex along this line segment, then what it means is that the original function f is convex. So v here is any directional vector. So the f should satisfy following property. For all v such that x plus t times v belongs to the domain of f, right? So we make a function g of t which goes to f of x plus t times v. So the domain of the function is a set of all t such that x plus tv belongs to the domain of f. So for all such t and v, if g of t is convex, then f is also convex. So this is one important property of convex functions. So for example, the original function f is a mapping from n-dimensional real vector to a scalar, whereas g of t is a mapping from a scalar to a scalar. And often, as you'd encounter if you're dealing with very complex functions, the original function might be very hard to prove convex, whereas the resulting scalar function might turn out to be very easy to prove that it is a convex function. So this property will be using this property when we derive the first order first order convexity condition for a function f. So now we'll study one more topic known as extended value extension of a convex function.